so that we can make sure that you still get full credit for it. Okay, so as folks are trickling in, we're going to get started with lecture 5, and this is linear models 3. And so this will wrap up our discussion of linear models and start into what will continue on for the rest of the class as we start to think about more and more complex predictive models for machine learning. And so today, as I mentioned before, some announcements. Homework 2 is out, so if you haven't already, please do take a look at it. The TA office hours for homework 2 have also been posted, so if you started working on it and have some questions about the problem set, please do go ahead and check out some of the TA office hours, as well as the ethics module pre-survey is out, and that's due October 16th, which is in 5 days. So today what we're going to do is an extension. So last week we spent a lot of time talking about the idea of binary classification. So we started off with binary linear classification, and after binary linear classification we went on to motivate the idea of logistic regression and the idea that you can learn logistic regression models via gradient descent. So when we ended with logistic regression, we were able to learn machine learning models that could correctly predict outcomes for a binary classification task. So we want to ask, how do we predict more than just 2 classes? How do we extend that to predicting k classes? And so that's what we'll talk about with softmax regression. The second topic we'll talk about is the idea of tracking model performance. And so far we've talked about training with the loss function, and the question then becomes, is that sufficient? What are the other metrics that are relevant to validating and analyzing machine learning models, both as you train them and after you train them, and how do you study those metrics? And finally, we'll talk about the limits of linear classification and introduce in today's lecture neural networks, which we'll cover in much more depth in next lecture. So let's get started. So as I mentioned before, last week we covered binary classification with binary linear classification as well as logistic regression. And really the task then was to predict a binary target. And now we're going to think about how to generalize that idea to predicting classes with more than 2 targets. So in general, here's 2 examples of data sets that have more than 2 classes. On the left is the MNIST handwritten digit data set, where if you zoom into this picture, you'll see that the goal is to take one of these images, so it's going to be a 28 by 28 dimensional box that you're going to be given as an image, and the goal is to predict what digit is in that image. So if you got this image, you might predict it's the digit 0. If you got this image, you might predict that it's the digit 2. And essentially, you have 10 classes to choose from in total, 0 to 9. So that's a multi-way classification problem that you want to solve. Another problem you may care about is, given this image, can you predict which object is in this image? So this is the task of object recognition. And here what you're shown are the outputs of maybe the top 4 most likely classes that exist in this image. So in this case, it obviously gets the answer wrong. But here is an example of a snowplow where the model is guessing the answer correctly. And so regardless of whether we want to classify digits or objects, what we need is a mechanism to be able to have the output of our machine learning model predict multiple different things, multiple different probabilities associated with the probability of any given class being in that input. And so that's how we're going to formulate this multi-way classification problem. To do that, we need to modify our notation for outputs. In the past, we've been happy to work with scalar valued outputs, where the outputs were a number if we were doing regression, or they were a binary label, so a 1 or a 0 if we were doing binary classification. But since we're doing multi-way classification, the outputs, the targets, form an element in a set 1 to k. So t is equal to small k might represent one target that is taking the value of small k, where k lies in the set 1 to capital K. So an alternative way, and the way that we'll use in this class to represent targets for multi-way classification, is to represent them as one-hot vectors or one of k encodings. And this is a really simple vector representation for a multi-class classification output. you know that your target is one of k different classes. So what you're going to do is you're going to take a vector of size k, and this vector is going to be a vector of ones and zeros. It's a binary vector. And all you're going to do is you're going to put a 1 in the entry that represents the kth class. So if you were doing MNIST digit classification, your k would be 10, and the first element might represent the fact that the object is class 0, the object is of an image 0, and the last one might represent the fact that the object is of class 9. And if there was a 1 here, it would represent an image that represented a 9, and if there was a 1 at the very beginning, it would represent an image that represented the image 0. And so if we have 4 classes, we will have a vector of size 4. And if the target is the first element of our set of possible class outputs that it could be, then the first element of this vector will be 1 and everything else will be 0. If our target was the second element of the set of possible class outputs, then the second element of this vector would be 1 and everything else would be 0. And so in this case, I've used 1 indexing notation. You could also equivalently do this with 0 indexing, and it would still remain the same. So just be careful, be consistent regardless of which notation you're using, but the principle remains the same. You're going to represent targets for a multi-class output as a vector that's mostly zeros with exactly 1, 1, and the location of the 1 tells you what class is in that object. Any questions about the one-hot representation or one-hot encoding for multi-class targets? Okay. So if there's no questions about this, then we're going to think about, as we did before, modeling multi-way outputs. So in linear regression and logistic regression, we performed a linear operation on our inputs in order to get a single scalar number. What we're going to do is continue to now perform a matrix vector calculation in order to get an output that is now a vector. Because remember, our target takes the form of a vector. So we would like a vector output as well from our model. So we're going to perform the operation z equals wx plus b, or if you were to incorporate a dummy variable into your inputs, you could perform it with a single matrix vector multiplication. And so W here is now going to be a k by d matrix, where k is the number of classes that you have, x is a d by 1 vector, and b is going to be a k by 1 vector. So k by d times d by 1 plus a k by 1 operation gives you that z is a vector that lies in k by 1. And so each element of this vector z, in some sense, represents the beliefs that our model has that the class is class k. So zk can be written as a summation over d of wkj, xj plus bk, for each of the k's ranging from 1 to k. So what are we doing really? In binary classification, we took our input, we multiplied it by a vector, added a bias, and then we predicted, and we passed that through a sigmoid operation to get the probability of the class being 1. But now we have multiple different classes. So for each class, we're going to do this vector dot product with our input. We're going to add a bias, and the bias is going to be different for each of the different classes, which is why you have k different b sub k terms. And that's going to give us the zk, the belief that our model thinks it's class k. So any questions about any of the algebra that's on the board so far, about the setup for how we take an input and we pass it through this linear operation? In this case, it's a matrix vector multiplication plus an addition in order to get a k-dimensional output from our model. Yeah? So it's not going to be k binary classifications, but you can sort of think of it as k prediction problems. So we're predicting k different things with this matrix as our parameters for softmax regression. Yes?
So in the final vectors, is that going to be like 0 in every k classes?
Not quite. So remember, the output of this operation z is still going to be a vector of k, where each element is going to be a real valued number, because we're not putting any constraints on what z can look like just yet. So it's just the result of a matrix multiplication with a vector, which can be any number in the reals. So you can have positive numbers, negative numbers for each of the zk. Okay. So I put up this set of additional slides just to make sure that folks are completely comfortable with this idea of this extension from logistic regression to softmax regression. So remember, we're going to consider a concrete setup where we have d is equal to a 2-dimensional input and k is equal to a 4-dimensional classification problem. So d is equal to 2, k is equal to 4. So specific numbers for choices of d and k. And for those choices of numbers, we have a W matrix now that looks like this. So I'm going to denote each row of my W matrix as W1, W2, W3, W4. And similarly, each element of my B vector as B1, B2, B3, B4. And this representation is useful because it's kind of easy to see why multi-way classification is like making k different predictions with this representation. Because what you're going to do in terms of doing this computation of z is equal to wx plus b is that for the first element z1, you're going to take your input x, take w1 and b1, and perform the linear operation corresponding to w1 transpose x plus b1. And you're going to put that in this vector z1. You're going to take x again, multiply it by w2 transpose, and add b2, and put the result in z2. And you're going to do the same thing for 3 and 4. So now this gives you this vector z, and remember z is also of dimension k times 1, which I'm just representing as a row vector here for convenience. Any questions about the computations that are happening under the hood when you transform from a vector dot product plus addition to a matrix vector computation plus vector addition? Okay. So hopefully the diagram is useful to tell you what's going on under the hood. But now we have a vector z, and z is in Rk. So how do we make a decision about which class it is? Well, if we think and interpret each of the elements of z as the amount of belief that the model has that the output is class k, remember the size of z is k, and in that case, that a really sensible decision rule is to set yi, our output, to be a vector of 1 if I is the argmax of this vector z, and 0 otherwise. So what we're going to do is we're going to look at our vector z, find the location of the largest element of the vector z, and because it's the largest element, we're going to claim that that's the model's belief about the correct class. So we're going to create our output as another one hot vector, which is going to be all zeros, except for 1, which is going to lie in the location where z has its largest element. So you can think of this as the prediction from our model as really the output that is in one hot representation. And so a question you can ask is, well, how does this k is equal to 2 case relate to the case of binary linear classifiers? Well, in binary linear classifiers, if you recall, what we did is we asked whether the operation of w transpose x plus b was greater than or equal to 0. And intuitively, what that was doing is it was simply checking whether that single vector-vector product plus addition was greater than some threshold or lower than some threshold. And that's equivalent, and I'll show you why in a few slides, to just thinking of the case where k is equal to 2. Like, let's say we only focused on these two elements. It's equivalent to asking which one is bigger. So y is really our decision that's going to come out as a consequence of generating this prediction from our z's. But remember, in order to do learning with this model, like last week, we went through several different iterations of coming up with a good loss function. for logistic regression. We had to go through the process of taking the output from our model and interpreting it as a probability. So we're going to skip a few of those steps and ask the question, how do you interpret the output of a model for a multi-way classification problem as a probability distribution over k classes? We're going to apply the same strategy that we did last week, but instead of just one number, we now have k numbers. And those k numbers represent, in the vector z, a belief about which of the k classes it is. So we want to take those beliefs and transform them into a probability distribution. So in order to do that, to soften the predictions for optimization, what we're going to use is a function. So just like we use the sigmoid function in the binary case, we're going to use the softmax function in the multi-class case. And the softmax function is very simple. It's a function that takes as input a vector, and it spits out a vector of the same size as well. And all it does to each element of the vector is this operation. So I'm going to show you the output of the softmax function at the kth element of the vector. So at the kth element of the softmax operation, it's going to look like e raised to zk divided by a summation over k prime e raised to zk prime. So before we dig deeper into what this is actually doing, the intuition you should have is that you're making all of the numbers in z positive, and then you're applying a normalization step to them. Because at the end of this operation, you should be able to verify that if you sum up all the yks, you will get 1, which is a property you need for a probability distribution to satisfy. So in this particular case, each input zk is referred to as the logit. We interpret the outputs as probabilities, and if one of the zk is much larger than the other, then it's approximately, then the softmax operation will set that to be approximately equal to 1, and it'll effectively start giving us the output that we care about getting. So remember, if I take a vector of real valued numbers looks like this, so let's say we had k is equal to 3, and the 3 elements of this vector were -2, 0, and 2. The application of the softmax operation would look like this. We would first exponentiate each of these elements. So that would give us e to the -2, e to the 0, e to the 2. And then we would sum up all of the elements of that vector to give us this, that I'm going to call z. And we would divide each element by z. So that's what I meant when I said y sub 1 or y sub 2 here is going to be e to the 0 divided by the normalization constant z. So just looking at this equation, you can verify the inequality that I wrote, the equality that I wrote before, which is that if you sum up over the y's, you will get 1 as your result. So one question to ask here is, why do we care about exponentiating? Like, if we just want a vector that sums up to 1, couldn't we just normalize it? Any thoughts? Why use the exponentiation operator? Yeah.
Because otherwise you have a negative number in the set.
That's right. So you'd have a negative number, and so you wouldn't be able to normalize it properly to ensure that it respected the relative beliefs of the model, unless you were working with either exclusively negative numbers or exclusively positive numbers. So to maintain the ranking of what the model believes are high probabilities and low probabilities, we perform a monotonic transformation via the exponentiation operation, which is going to preserve the orderings, and then we normalize that resulting vector, and that's what the softmax operation does. So hopefully you're convinced by now that this is at least going to give us a probability distribution over the different outputs from our prediction model if we pass z into this. And this lets us sort of think about how we can compare to the case where k is equal to 2 in binary classification. So to compare to the case where k is equal to 2 in binary classification, we have sum x, which is a linear input. We're going to get z1, what I'm calling z sub 1 and z sub 2 are the elements of the vector z that are going to be obtained by doing the matrix multiplication with the vector input and adding in the vector of the biases. So I've just split that up here. So this gives us z1 and z2, and we'll apply the softmax operation to get this quantity in YMC, the multi-class probabilities. And our decision rule is to pick the argmax of the two, or to figure out which of these two is larger. And if we were doing binary classification, we would simply check whether this was bigger than some threshold. So another way to map these two functions together is to look at the ratio of the two of them. Because the ratio of the two of them, if it's greater than or equal to 1, tells you that one is bigger than the other. So this should be 1 and not 0. And so we can do y1mc divided by y2mc, and the denominators cancel out to give us e of z1 minus z2. And we can substitute in the formulas for z1 and z2 in here. And if we simplify, we get e of this quantity times x plus this quantity should be greater than or equal to 1. And what that's really saying here, this should be a 1. And what this is really saying here is that this is equivalent to binary classification, to the decision rule that we had for binary classification, where the W that we would have used for binary classification can really be seen as the difference between W1 and W2 in the multi-class case. And similarly, the bias for binary classification can be seen as the difference between the bias 1 and bias 2 in the multi-class classification case. Any questions about this? Yeah.
Could you run through mapping again this once more? I'm a bit confused about the second last line again.
This one?
Yeah.
As to how I got from here to here?
Yeah, essentially.
So I just substituted for Z1 this quantity. This is the definition of what Z1 is. Similarly, this is the definition of what Z2 is. And then I pooled terms together.
Okay.
So I got W1 minus W2 transpose X.
Oh, okay, transpose X.
Yeah. And then plus B1 minus B2.
Yeah.
And I just interpreted the difference as the vector WBC.
Okay, that makes sense.
And so just as we had the cross entropy in the case of logistic regression, we're going to have the softmax cross entropy as our loss function. And in the binary case, remember what we did was negative t log y minus 1 minus t log 1 minus y. And remember, in the binary case, y was the probability that the model predicted a 1. So 1 minus y was the probability that the model predicted a 0. In the multi-class case, we directly have the probabilities or the beliefs as predictions from our model. So we're going to do an element-wise multiplication of the log of these probabilities, the negative log of these probabilities, with our target vector, and we're going to sum it up. And that can be compactly written as this equation here. So we're going to take each t sub k, so that's going to be one element here, and we're going to multiply it by negative log times y sub k, which is going to be one element here. And you can compactly write down the calculation of this loss function as computing negative t transpose log y, where each of these two, both t and y, are vectors. And so just as we did for the cross entropy of the binary case, there's also a variant of the softmax cross entropy that blends together the softmax function with the computation of the cross entropy loss. And so we're now in a position where we can actually derive the gradients with respect to the parameters of our model. So for softmax regression, we have z is equal to wx, the matrix multiplication. We get our vector z, pass it through the softmax operation, and then we get a vector of probabilities as outputs from our model, where y is in Rk, where each element of y represents the probability that class k is in that input. And then we perform this vector dot product with the negative log of y and t transpose, where t is our one hot representation of the output, to get the loss function. And then the process is exactly the same in the context of learning this model as we did with logistic regression. We're going to use and derive gradients with respect to the gradients of this loss function with respect to the parameters of our model. And so the parameters of our model now is not a single weight vector k, but k different weight vectors and biases. Because we have k different rows of our matrix W. So the derivative of this loss with respect to one of those rows is going to look like this via the chain rule. So the derivative of the loss with respect to z, and the derivative of z with respect to the weight. And so this operation, the derivative is just x, the input, and the derivative of the loss with respect to zk, for very similar reasons as we had derived for the cross entropy as well as for mean squared, takes the form of the difference between the prediction and the target. So this is a scalar, and this is a vector. And so the derivative of the loss with respect to the weight is a vector, which has the same dimensionality as the input. So d. Yes? So when we use this bold notation, it's a vector, and when we use t sub k, it's the kth element of that vector. Yes, t is a one hot vector. And so what this entire setup lets you do, and then after that, this is the standard update rule that you would use for learning via gradient descent. So this is the process of deriving gradient descent update rules for softmax regression, which allow you to generalize from the binary classification case to the softmax classification case. So I'll pause here to see if folks have any questions about anything I've covered so far. Yeah. Oh, that's a, yeah. So your question is, let's say in our data set we only had MNIST digits from 0 to 4. So we had 5 digits. And so k was 5 in that model. What do we do when we get a digit that looks like a 6? The answer is you'd have to modify your model in some way. You can't use the model that you've used as is, because it has no notion of what a 6 is, because it's never been trained to recognize it. So one operation that you could do is you could take the model that you've learned over 5 classes and use that as a starting point to learn a model over 6 classes. So you can initialize the weights to be the same so that you transfer knowledge from what you've learned on the previous task and then continue learning with the 6th object. Okay. And so what we're going to talk about now is the idea that when you have this formula that we've created, build a model, come up with a loss function, take gradient descent updates with respect to the loss, and that's how you do training. You also have to ask, how do I know that I've gotten a good model to begin with? And so we're going to take a minute to talk about tracking the performance of models. So as I mentioned before, it's really, really important to make sure you track the progress during learning by plotting the training curves. And we often choose our training losses in part to be easy to optimize. Because remember the exercise that we did with binary classification where we thought about the 0-1 loss. the 0-1 loss was really intuitive, but it was not differentiable, so we didn't use it. But it represented an intuitive quantity, the misclassification rate, which is still a worthwhile number for us to know when we're training the model. So we often wish to track other metrics to assess the performance that we get with our model, even if we're training with a different loss function. And so one such metric for binary classification is accuracy, which corresponds to the averaged 0-1 loss. And so this is just a fraction of correctly classified points for binary classification. But in binary classification, you can actually break down what correct means into 4 categories. So you could create a table that looks like this, where the columns represented the true class and the rows represented the predicted class. And for your validation set, you can look at the number of times the predicted class is 0 and the true class is 0. And the predicted class is 1 and the true class is 1. And you're going to call that the true negative and the true positives. And you can look at the number of times the predicted class is 0, but the true class is 1. So you're going to call that the false negative. And similarly, you're going to call this the false positive, because this was where you predicted the class to be a 1, a positive, but it was actually a 0. So you can create this table, and this table has a really useful set of way to break down the quality of results that you're getting from your binary classification model. Because you can write down accuracy as a function of elements that exist in this table. And so if you take further classes in statistics, you'll hear terms such as type 1 error and type 2 error, and they effectively, for a binary classifier, correspond to terms that arise from this table. So things like the false negative is a type 2 error, and false positive is a type 1 error. But it's really important to keep these concepts in mind, because depending on the predictive problem you are actually solving, they can come in very handy. And so we're going to think about a potential exercise where we want to build a machine learning model that would predict whether someone has a disease. So it's a binary classification task. 1 represents has disease, 0 represents no disease. For this binary classification task, what we do know is that 1% of patients have the disease. So it's a very rare disease. So if you had 100 training points, only 1 of them would be positive. What's the simplest model that can achieve 99% accuracy? Yeah. That's right. So just a constant function of predicting 0 achieves 99% accuracy on this data set. So what does that tell you about accuracy as a metric? It tells you that it has limitations in terms of utility when you're working with imbalanced classes. And so what people often do is come up with different metrics that are useful even under class imbalance. So 2 such metrics are called the sensitivity and the specificity. So sensitivity is how often you see a true positive as a function of the number of total predicted positive elements that you have by your classifier. How many of the times you predicted that there was a positive was there actually a positive? And similarly, specificity is true negative rate, which is of the times that you predicted a 0, how many of them were actually 0? So remember, if you have perfect classification, your false positive rate and your false negative rate go to 0, and you're left with 1 on both of these. So if you have perfectly linearly separable data, you have 1 on both of these metrics and you're golden. The problem comes about because you don't have perfectly linearly separable data in practice. So what do you actually do? How do you pick a threshold to decide which ones are going to be 0 and which ones are going to be 1. Because remember, the output of your binary classifier logistic regression is a probability. You need to choose a threshold so that anything above that probability threshold is said to be a 1, and anything below that threshold is said to be a 0. So how do you pick that threshold? Well, one way to decide what that choice looks like is actually to consider not one threshold, but every possible threshold that you could pick. So remember, you're predicting whether or not someone has a disease. So the population that you care about predicting, some people have diseases and some people don't. And what this plot is showing you is what happens to these different numbers if you were to pick this as your threshold. So this other set of people, so you take all the people who don't have the disease, you pass them through your classifier, and you look at where the probability of their outcome falls on this real line, and you do the exact same thing for all the people who do have the disease. And that's how you get these curves. And now what this is saying is if you were to choose this particular split or this particular threshold, then the number of true negatives you would incur is going to be represented by this area. So this is the total number of true negatives. This is the total number of true positives. And similarly, this is the false negatives and the false positives. Because everyone to the right of this threshold is going to be predicted with a 1, and everyone to the left of this threshold is going to be predicted with a 0. And what you can visualize is what happens when you move this threshold from left to right. So let's say you put the threshold here at r is equal to 0.01. If that was your threshold, then you would have a classifier that almost always predicts that everyone has the disease. So you would have the number of true positives you would have is very large. But so too would be the number of false positives. Because for everyone who did not have the disease, you would still have a very high number of people for whom you said that they did have the disease. And if you map the process of going and changing this value of r, this threshold for our binary classifier, from 0 to 1, and you plot the true negative rate and the true positive rate, sensitivity and specificity, you'll observe that they behave according to this trade-off. Because in this trade-off, for small r, you might have a very high true negative rate, but a very low true positive rate, and vice versa. So remember, we started out this discussion by asking what happens when you have imbalanced labels in binary classification. We talked about the idea that when you have imbalanced labels and your data set is not linearly separable, there's this notion of a trade-off depending on how you pick your threshold for your binary classifier. This threshold trades off between sensitivity and specificity. And what you can do is you can plot this threshold. So you can plot what would happen to the true positive rate and the false positive rate for every choice of threshold that you could choose. And if you were to visualize that plot, you would get what is called the receiver operating characteristic curve. And what this curve does is that it enables you to summarize what that trade-off looks like. Because by looking at the area under the receiver operating curve, you can actually tell how well a model balances that trade-off. Because a random classifier is going to have a small area, and it's going to correspond to the diagonal line. And a perfect classifier is going to correspond to a step function. And in practice, most classifiers will be somewhere in the middle of these two. So you'll have a number that lies between in practice 0.5 and 1 that quantifies how well your binary classifier balances the trade-off between sensitivity and specificity when you look at the area under the receiver operating curve. Okay, Any questions about this so far? Yeah.
I understand that after we train our model, we can then pick a threshold value based on whether we want to minimize our false positives. Or true
That's right.
negatives. But is there a way we can tell our logistic regression model to penalize false positives more heavily than penalizing true negatives?
That's a really good question, and the answer to that is yes, and it's not something we'll cover in this class, and it's something that a lot of advanced machine learning classes go into. So there are tools that you can use. You can regularize your model to create auxiliary loss functions that encourage exactly the kind of behavior that you'd want to minimize the false positive rate or to minimize the true negative rate. Because if you know a priori that you would prefer one over the other, given that there exists this trade-off, you might want to encourage your model to explicitly learn that when it's training. An example of that is, imagine you're building some kind of a predictive model that's going to be used in a hospital system to figure out an alarm when a patient is about to die. So for that kind of alarm, you might be okay with a few false positives, but you definitely don't want false negatives, because a false negative would mean that you miss the possibility that this patient might die, and that has catastrophic consequences. And there's also scenarios where the reverse is true. So it's often a domain-specific question depending on how you're deploying this classifier. So like if you were to go work at Netflix, they might have different domain-specific constraints that require you to balance these two. So it's definitely a concept worth knowing about. And often, to answer your question, actually, a really easy thing that people can do when they're training a logistic regression classifier is use and plot these metrics on the validation set and use a technique called early stopping to stop training when they've reached a good trade-off between false positive versus true negative rate. Okay, so we talked about evaluating binary classification. What about multi-class classification? A really popular tool that you should all be familiar with is what is called a confusion matrix. So as the name implies, it is basically a matrix that tells you what your model is confused about. So on the rows are the predicted class, on the columns are the predicted class, and on the rows are the actual class, so the true labels. And in this case, this is showing you the confusion matrix for the MNIST digit classification challenge. So our goal is to build a predictive model that can predict whether a digit is 0 to 9. So whether it's a 0 or 1 or all the way up to a 9. Every time our model gets an answer correct, which is to say, if a digit is 0, our model predicts a 0, we're going to add 1 to this element of this matrix. If the target is 5 and the model predicts a 5, we would add 1 to this element of the matrix. So think of this as like a matrix as a bunch of counters. Like those counters are just going up, and the location of the counter is telling you whether the model is doing something right or wrong. So for example, what this 7 means is that on the MNIST dataset, there are 7 examples of the digit 8 that were incorrectly confused by the model to be the digit 5. And so looking at this matrix is often a really useful tool, because you should always expect that a model that is actually correctly classifying things has a majority of the numbers on the diagonal. And unlike the true positive and true negative rate, it gives you a much more fine-grained analysis of where the errors are that the model is making. In this particular case, it tells you which classes are being confused for one another. So any questions about the evaluation of machine learning models so far? Yeah.
Still for clarification. So on the right side,
Yeah.
that is like the number of actual zeros, ones, twos there are. And
That's
at
right.
the bottom, it's the number of the number of predictions, 0, 1s, 2s that we did.
That's right. So the number 97 here is obtained by summing up 90 plus 2 plus 1 plus 4. So it's saying in total, the number of actual zeros are 97, but the model predicted that the data set had 101 zeros. And so summing up along the columns is summing up the total number of predictions made by the model.
And the sum of every element is the size of the data set?
The sum of all of these, of both the rows and the columns, should be the same number that is the size of the data set, whether it's the training set or the validation set. Yeah?
In the binary case, we have a threshold that we can change. So for this computed matrix, how do we update our model when we see these out?
Yeah. We won't talk about this, but there's a whole subfield of machine learning that deals with a question called calibration. And calibration says, like, when you're training machine learning models, you're going to look at average accuracy, which is how well it does on average across this data set. But what you also want are the relative fractions of different classes to be comparable in the predicted set and the actual set, which is information you get from looking at something like a confusion matrix. And there's tools called plot rescaling and temperature scaling that are devised to ensure that the model's predictions are well calibrated with the population level frequencies of different label distributions. And so if you're interested in that line of work, I encourage you to check out this idea called calibrating classification models. Okay, so I think this is a good place for us to take a 5-minute break. We'll start back up again at 2:02 when we'll continue talking about limits of linear classification. Hey.
Good afternoon. I just wanted to ask, with respect to homework 2, after today's lecture,
You should be able to do it. Yeah.
I should be able to do
Yeah.
it. Do I need the tutorial to do it?
I think it's.
Concentrate on Python.
Yeah. So I don't think you need the tutorial to do it, but you will need it for homework 3.
Yes.
Yeah.
That's all I wanted to confirm. Thank
Cool.
you so much.
Yeah. Just.
And while I'm still here, is it okay for me to keep asking questions?
Yeah.
Alright, so I will not lie. I got a bit confused between the Y's and the T's, right? Because over here you mentioned that you're basically binarying Y. You're dealing with Y as zeros and ones.
Yeah.
But then you also mentioned about Y being represented as a set of probabilities.
So remember.
Sorry, vector probability.
Yeah, so this is the binary linear classification view of the multi-class classification, and this is the logistic regression view of multi-class.
Okay. So once we get the values from Z, over each element we apply the softmax function, and then we pick the max of that softmax function?
Yeah.
Okay.
And it will be identical to this.
Yeah,
it's
yeah,
just
it's
that
not-
you can
yeah.
interpret them as
All right, okay,
probabilities
that's-
so that you can optimize them with gradient descent.
Fair enough. Thank
Yeah.
you.
Hey.
Sir, could you help me with for the core 318 as a over British question?
How long will it take?
About like 2 minutes.
Sure. Yeah. What is it called? What is 318?
I think it's has topic related to
What are you trying to do your project on?
it's actually my friend's project, so
Oh, you're just helping out.
yeah.
Okay, let me just check what this course is for. Interactive computational media. This one?
Yeah, that one.
Who's teaching it? Is this? I don't know what you pressed here. Sorry. Which one is forward? How do I go next?
You just submitted.
Oh, okay.
You
great.
finished?
Yeah.
Okay.
Cool.
Thank you for the help.
Yeah, you're welcome. Okay. So I think we'll get started again. Last week when we talked about the idea of binary linear regression, binary classification, we talked about this notion of linear separability. And what we showed last week was that the not function and the and function are linearly separable. And what that means is that you can come up with the equations to represent a hyperplane such that if you were to draw the hyperplane in the space that the data points lay in, anything to the right of the hyperplane would be all one class, and anything to the left of it would be the other class. But there's some data sets, such as the XOR data set, that are not linearly separable. And so if you were to plot the XOR data set, you would end up with something that looks like this, where you have 0, 0, 1, 1, both having 0, so they've been labeled with the negative class. So the truth table for XOR is 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0. So this is the XOR function over two Boolean variables. And that's just visualizing what the XOR function looks like. And if you have this function, it's not really possible to come up with a line that is going to be set up in such a way that everything to the left of it is going to be one class and everything to the right is going to be the other. So this line doesn't quite do it, nor does this horizontal line. And you can start tilting things vertically, but you'll find that it's impossible to do so. So visually, this looks intuitive and obvious if we were to visualize the data. But how do you mathematically prove that XOR is not linearly separable? So to prove that something is not linearly separable, it's worth remembering how we proved that something was linearly separable. We effectively took each data point and we mapped it onto a separating hyperplane. So we took each of our training points and we applied the binary linear classification rule to it, and that gave us a set of inequality constraints in the weight space. And we said that something is linearly separable as long as the set of linear inequalities represented a feasible region. So we're going to use a similar style of analysis, but we're going to perform a proof by contradiction. And so we're going to use the property that half spaces are convex sets. So any half space is a convex set, which means that if 2 points lie in a half space, then the line segment connecting them must also lie in the same half space. So we're going to pretend that the data is linearly separable and that points that are in the same class lie in the same half space. Yes? So when you have, let's say you're in R2, you come up with some separating hyperplane here. Everything to one side of it represents a half space. And the reason why we care about half spaces is because we're working with linear functions. And so remember, in last week, each training point gave us a half space. Like it gave us an equation of the form W1 plus W2 greater than or equal to 0. And that equation represents a half space in weight space. And so the question, and so because it cuts up the space of our data into two sets. So that's why it's called a half space. And it turns out that half spaces are convex. So any half space is a convex set, which means that if 2 points lie in a half space, then the line segment is also in the same half space. And this is a proof by contradiction. So we're going to close our eyes and pretend that all the positive points lie in the same half space by some theoretical possibility of a separating hyperplane. So we'll pretend that there exists a separating hyperplane that separates out these two half spaces where all the positive points lie and all the negative points lie. And because they lie in the same half space, it must mean that the positive examples are in the positive half space. And so every point in the green line which connects the positive examples must also lie in the positive half space. And the same converse argument holds true for the negative points. If both of these negative points are in the negative half space, then any line segment connecting them must also lie in the negative half space. But you reach a contradiction when you notice that these lines intersect, because the point at the intersection cannot, by definition, lie in both half spaces, which is the contradiction, and therefore the initial premise that the problem is feasible is flawed, and therefore your data set is not linearly separable. So any questions about this proof by contradiction for proving that something is not linearly separable? Yeah?
So this is with respect to just 2 points in each half space, right?
Yeah.
Now, what if you had multiple points in that half space such that one straight line couldn't go through all of them?
It doesn't matter, because you only need the proof to work for any pair of points.
Okay, all right.
Because remember, linear separability is a strong condition. It says that for all pairs of points, there exists this plane such that you can separate the positives from the negatives.
All right.
Yeah. In this case, we just did a proof by picture, but in certain cases, you might just have to show that there's an intersectional point. You can write algebra to find a point that lies in both, that lies on both line segments. Okay, and so what do we actually do when points are not linearly separable? So in the second week of lecture, we talked about the idea of polynomial regression. And what we did there was we made use of a feature map. And so we took our original space and we expanded it out into a much larger feature space. And doing so enabled us to model complex polynomials really well. Can we use the same idea in the case of the XOR function? And it turns out that you can. So I won't prove that this data set is indeed linearly separable, but if you look back to last week's lecture, you have the exact formulas that you need in order to punch through the math to show that this is linearly separable. But this choice of feature map of x1, x2, x1, and x2 results in a new data set. So this is your original data set before the feature map. This is the XOR data set. So you want to learn a function to map from this to this. And you know, we just proved that it's not linearly separable. So what you're going to do is you're going to take this data set, you're going to map it through this feature function, And that's going to give you this new data set. And it turns out that this new data set is linearly separable. So if you were to learn a binary linear classification model on this data set, you would find that you could perfectly classify XOR. And this shouldn't surprise you, because if you've taken classes in Boolean logic, you know that XORs can be composed of various different simpler functions like ands and nots. And that's basically the strategy that we used in order to come up with this feature map. So designing these feature maps can be quite hard. The question we want to ask is, can we learn them? Because if we had a hypothetical mechanism to learn a feature map, then that's a really useful thing to have, because we don't have to hand design feature maps so that data points, when mapped to this new feature space, end up being linearly separable and easy to solve. And so that's really the context in which we'll introduce neural networks. And so the remainder of this lecture and next week's lecture is going to be dedicated to thinking and learning about neural networks. And so neural networks were really sort of inspired originally by thinking about computations that happen in the brain. So in the brain, you have neurons that respond to certain stimuli. So whenever there's a stimuli, you have a chemical response that triggers the neuron to fire, as well as after firing, go back to some notion of a resting state. And people really wanted to mimic this idea of a neuron firing in a computational system, because they felt that it might present an interesting abstraction by which we could build large machines that learn correctly. So how do we think about building an artificial neural network? Well, for neural nets, we use a simpler mathematical model for a neuron, and this is going to be called a unit, where if we had, for example, a three-dimensional input, we're going to do a really simple operation for a single neuron. We're going to take our input, we're going to multiply it by a vector of weights via a dot product, so W transpose X, and then we're going to add a bias. So this is something we've seen 3 to 4 times already, so you should be very familiar with what that operation looks like. And then we're going to apply an element-wise nonlinearity or an activation function. And so it looks really similar to logistic regression. So the formula for logistic regression is basically this, where y is equal to a sigmoid function of W transpose X plus B. And you can think of the sigmoid function as sort of the activation function in the context of logistic regression. And this is what we view as a single neuron. And in a neural network, what we're going to do is we're going to create a network of neurons. We're going to throw a lot of these different units together to create a directed acyclic graph. So this is the first neuron, the second neuron, and the third neuron in what is called the first hidden layer, and the first, second, and third neuron in the second hidden layer, whose computations are going to be leveraged to predict the output at the output layer. And so the units, each neurons are grouped into these layers that represent regions where parallel computation happens, and the output is going to be the output of the neural network. So if we wanted to see what this neuron would do, then what this neural network would do, we would pass through it an input, and via the matrix multiplication plus activation function operation that I showed you in the previous slide, we would compute H1, H2, H3 in the first layer, and now we have all the pieces that we need to compute the hidden layer in the second layer, and then we would repeat that at the output layer. And so this is an example of a neural network that has depth 2, so it's a 2-layer neural network. And in general, a multi-layer network or a multi-layer perceptron consists of these fully connected layers. Why are they called fully connected? Because every neuron in layer L is fully connected to every other neuron in the layer below it. So that is what a fully connected layer does. All input units are connected to all output units, and each hidden layer I connects to ni-1 input units to ni output units. And what that means, remember when we talked about using softmax classification, we had a vector of inputs and we wanted to predict a vector of outputs. So we did that via a matrix vector multiplication. In just the same way, we're going to have these matrices as our weights or parameters of this neural network. In each weight matrix corresponding to a layer, we have a ni times ni minus 1 dimensional matrix. And the operation can be compactly represented as y is equal to f of x of phi, which is some element-wise nonlinearity that is applied to wx plus b. So rather than computing things neuron by neuron, you can compute things layer by layer. And this is showing you the computation of the first layer of this neural network. So the first layer of this neural network is going to take as input the input vector. It's going to multiply it by a matrix W, whose output dimensions are going to be the number of hidden units in the first layer. And then you're going to add a bias term. And then you're going to apply an element-wise nonlinearity. And that's going to be the output of the first hidden layer. So I'll pause here to see if folks have any questions about what a neuron is, what a neural network is, and how we went from a neural network to thinking about the computation in a single layer of a neural network via a matrix vector product plus addition. Yeah? You can, it becomes a little bit harder. You can do it at the input layer. At the output layer, you would have to artificially pad your hidden representations with a set of ones, but you could do it that way as well. It's just notationally a little trickier. So we stick with the W transpose X plus B. Any other questions about neural networks or the computation in each of the layers of a neural network? Yeah.
So each layer does its, from what I understand, each layer is doing its computation using data given from the previous layer.
That's right. So each layer's computation is done using the output of the previous layer's computation.
Which happens to be now the input of the current layer.
Correct.
Yes, and then it sends in that as an output for
The next layer and so on.
next hidden layer and so on.
And so we can think about what are activation functions and what should they look like. So some common ones include things like the identity, the rectified linear unit, which is the max of 0, z. And if you look at what this function is actually doing, it's really just squashing any signal that is negative and letting any signal that is positive pass through. So it acts as a nonlinear filter for positive signals and then leaves negative signals behind. Or the soft ReLU, which is a softer approximation to the ReLU. Especially when we're doing things like theoretically understanding neural networks, we often use things like the hard threshold activation function or the logistic function or even the hyperbolic tan H functions. So in general, there's a few different choices of activation functions here, but empiricism has largely driven the choices of what activation functions people use in neural networks today. There's not really a lot of theory that I can point you to that would suggest that one is better than another. And there's much, much more complex ones that are present in modern neural networks. So the flow of computation says that you start with an input, you do your matrix vector computation, you get the first hidden layer, you do another matrix vector computation, you get the second hidden layer, and you keep doing this until you get to the L-1th, the penultimate layer. And then, depending on what task you're solving, your output layer is going to differ. If you're solving a regression task, what you're going to do is you're going to have a simple vector matrix multiplication plus addition operation, because you want your output y to be a scalar that lies between negative infinity and infinity, because you're doing regression. If you were doing binary classification, or you might want to use the sigmoid nonlinearity at the final layer. And if you're doing multi-class classification, you would use the softmax function at the very last layer. So depending on the use case for your neural network, your output layer is going to change as well. Yeah?
So the hidden layers inside the activation functions for those aren't really dependent on what you want. So it's like there's like a standard for what happens in those.
What do you mean by it doesn't depend on what you want?
Because you said that if you want to do regression, like logistic regression
Yeah.
versus like classification versus regression, our final layer is going to do two different things.
Yeah.
But the hidden layers, do they still do like the same stuff to the inputs?
Yes. And so your choice of potential nonlinearity at the output is often independent of what you do in the middle. And so another point to keep in mind is that each of these different layers of the neural network has different weights. So in softmax classification, we had one matrix W and one vector of biases to take our input and map onto a multi-way classification output. But now we have L different matrices and biases that we need to keep track of as the parameters of our neural network. So we have many, many more parameters than we do in the linear models. More questions? Yeah. Yeah, so you can mix and match activation functions, but I find that given that the choice of which activation function to use is often treated as a hyperparameter, and that's picked on the validation set, people use the same one for convenience. Yep. Yes, but there's no rule that I can point you to determine what that should look like. Like, mostly that's derived from trial and error. Yes?
So what we do here is just repeat the prediction process again.
Exactly. So the kind of computation you do is going to be identical in each of the different layers.
So the number of outputs for each hidden layers will be the same, right?
That's a great point. You don't actually need to have the same number of outputs at different hidden layers. You can have hidden layers that are thin as well as hidden layers that are very wide, and the only thing that would change is the size of the matrix that you have at each layer. So let's say in this particular example, you could have a d is equal to 3 as the dimensionality of your input, and you could have h is equal to 5 in the first hidden layer, and then h is equal to 10 in the next layer. And what that changes is that this matrix will have dimensions 5 by 10, but this one will have dimensions 3 by 5. So it's really the dimensionality of this matrix that and the biases that end up getting changed by changing the widths of the hidden layers across different layers. But the kind of the equation for the computation is the same in a fully connected neural network.
So we decided the dimension of each layer by changing the matrix.
Yeah, that's right. They're equivalent. Okay. And so if you think of what this network is doing, it's really computing a composition of functions. So in the first layer, you compute one function that maps your input onto some new representation, and then you take the result of your first layer and pass it through another function, f2, and you keep doing this L times. So you're learning this composition of functions. And as you mentioned before, because we're doing the exact same computation at each layer, this enables us to leverage modularity because we can implement each layer's computation as a black box. Because you don't need to write, when you implement a neural network in code, you don't need to write L different computation steps. You write a function to do a matrix vector multiplication plus addition, and then you just reuse that function in a loop. Because all of the different layers L are performing the exact same operation. You just need to make sure that the right matrices and inputs are passed in. And so we can think of neural networks that learn these composition of functions as a parametric way to learn features. So we can think of what this last layer of representation might look like. And intuitively, the goal is to transform data that kind of looks like this, which is clearly not linearly separable, into data that looks like this, where the representation of the data is in a different form that enables you at the very output layer to do easy classification or easy regression or easy multi-way classification. And so suppose we're trying to classify images of handwritten digits, and each image is represented as a vector of 784 pixel values, then you can actually visualize what the first layer of a neural network learns. And it turns out it learns these diagonal slide prediction rules. And if you visualize many of them together, you see shapes that look like this. So if you zoom into one of these, you'll see that there's not much on the edges here, because in the MNIST dataset, there's not much information content on the edges of the image anyway. So those are learned to be ignored. Whereas a lot of the variation in how images shapes take place happen in this middle region of the image. And that's where you learn things like these curves or this edge or the diagonal edge that we talked about. So you can sort of think of these matrices as learning very low-level coarse-grained features, and each of the neurons in the first layer is activated when one of these features becomes activated. So you take one of these matrices and you check whether your image has this pattern in it, and if it does, you activate a neuron in the first layer. And by composing and doing this operation multiple times, it turns out you can learn a feature representation that's really, really useful for doing prediction. So unlike hard-coded feature maps, features that are learned by neural networks adapt well to the patterns that exist in data. Because we didn't, as humans, tell them to learn edge detectors or detectors of curves. It was learned automatically by training on a large data set. So that's what it means to have a feature detector that is trained, that is learned via data. And so we talked about this notion in the past of a hypothesis space. And so the hypothesis space is sort of the set of functions that can be represented by some model. And if we have two models, A and B, that have hypothesis space HA and HB, and if HB is bigger than if HA is bigger than HB, then we say that A is more expressive than HB, which is that A can represent any function f that lies in HB. So we know that some functions XOR cannot be represented by linear classifiers. Are deep networks more expressive? To answer that question, it's worth thinking about a very extreme case of neural networks. So a very extreme case of neural networks is the case where we use a linear activation function, or even simpler, the identity activation function. If we have the identity activation function, then the equation that you would run when you do the computation for a neural network would basically be W3 times W2 times W1 times X, because there's no nonlinearity in the middle. And so you would be doing a sequence of matrix multiplications. And this is no more expressive than performing a linear operation. And so the reason why is because you could represent the product of these three matrices by an equivalent matrix W prime that you could posit could have been learned via a linear predictive model. And so deep linear networks can only represent linear functions, and so they're no more expressive than linear regression. Which is to say, if you had this as the family of linear models, then you would have f from a deep linear model be within that family. But the moment you start adding in nonlinearities in the form of activation functions, you start exploring the space of HA, which is a much larger and richer space of hypotheses for your function. And so It's worth recalling the first and second week of lecture when we talked about what the goal of supervised machine learning is. Like, what is the Bayes optimal predictor? It's matching the conditional expectation of some t given x. And what we want to do when we consider nonlinear predictors is give our model as good of a shot at finding a function that matches that conditional expectation as closely as possible. And there's lots of scenarios in which we might not be able to find it. But the goal that neural networks rely on is the idea that we might be able to use the data to learn features that simplify the learning problem in a manner that helps us solve the task at hand. So by searching over a much larger and richer space of learnable feature maps, we can train these really, really powerful classifiers. And so multi-layer feed-forward neural networks with nonlinear activations are what are known as universal function approximators. And so they can approximate any function arbitrarily well. And so we're not going to dive into the theory of when and the conditions or what the theoretical results look like, but I can point you to the reference if you're interested in that. And this is true for various choices of activation functions. So for thresholds, logistic, ReLU, etc. And so what we're going to do now is think about the original problem that motivated this, the idea of learning feature maps for the XOR function, which we said was not linearly separable. And we manually gave an example of a feature map that made it linearly separable. But can that feature map be representable via a neural network? And so we're going to assume that we're using the hard threshold activation function. And so the hard threshold activation function is the identity function where there is some condition here. And if that condition is active, then the threshold activation spits out a 1. And if that condition is not active, then it spits out a 0. So it's a very simple activation function. It's a step function. And so my claim here is that this choice of parameters for the neural network with a hard activation function is going to perfectly solve the XOR classification problem. So first of all, let's learn to interpret what this neural network is doing. So I'm going to take a Boolean input. Whenever I have a 1 on this edge, it is representing the weight on that edge. So remember, all of my operations are of the form W transpose X plus B. And here, X is two-dimensional, and so W is two-dimensional. So if I wanted to get at the equation for H1, what I would do is do H1 is equal to 1 times X1 plus 1 times X2 minus 0.5, and check whether this is greater than 0. So that's what the hard threshold activation function would do, where this minus 0.5 denotes the bias. So this edge that has no input, it's denoting the bias for that neuron. So this is H1. And what you can do is you can actually verify that this is going to compute the OR operator for Boolean variables x1 and x2. So you can ask, when is this condition met? Well, this condition is only going to be met when both x1 and x2 are set to the value of 1. And so for every other value that they could take, it's going to be 0. So that you'd get a truth table that says 0, 0, 0, 1, which is the OR operator. We can do the exact same thing for H2. We can take x1, multiply it by 1, plus x2 multiplied by 1 minus 1.5, and apply the hard activation threshold here. And we can ask, when is this neuron active? Well, this neuron is active only when you have minus 1.5 and, oh, actually, I apologize. The first one is your the OR operation, which is actually active when either x1 or x2 is 1, because 1 minus 0.5 is greater than 0. That's my mistake. But this one is only active when they're both 1. And so this represents the AND operation. So you have H1 representing OR, H2 representing AND the claim is that you can solve the XOR problem as H1 and not H2. So remember I said that Boolean operations like XOR can be decomposed into simpler ones, and so this is a decomposition of the XOR operation into AND NOTs and ORs. And so what this is going to do, to implement the NOT operation, we're just going to multiply the output of H2 by -1. So the output Y is going to be H1 times 1, H2 times -1 minus 1.5. And so we can ask, when is this condition greater than 0? And that's a little harder to read out, like for me to read out manually, so we're going to look at the truth table for what that looks like. So what I've done here is given you all the possible values the input can take, and I've done the process of calculating what H1 would do, what H2 would do. So that represents, H1 represented the OR function, H2 represented the AND function. This is the operation of negating H2, so multiplying it by -1. And this is the operation of taking H2 and computing the AND with respect to H1. So if you just look at this and you compute the AND with respect to this, visually you'll be able to easily identify that the Boolean operation that this implements is identical to the XOR function. So what did we just demonstrate in the last slide? What we showed is that there exists a configuration of weights with the hard threshold activation function for a neural network to do perfect classification on the XOR function. And in fact, there's actually a notion of universality here, which is to say that using the hard threshold hidden units and a linear output, you can actually approximate any Boolean function over D variables. So I'll give you an approximate proof sketch here on how to do that. And the way you would do it is if you had D variables as your input, what you would need to do is set up the weights and biases for 2 to the D different neurons in the hidden unit. And each of the 2 to the D different neurons in the hidden unit would represent one element of the truth table for the function that you cared about approximating. So this neuron would take the value of the target of this function at one of the rows in the 2 to the D dimensional truth table. And if you were to do this across this obviously exponentially wide neural network, you can approximate any Boolean function over D variables. So it's a really interesting exercise to actually do this for the XOR function, because you can compare and contrast the neural network that you get for the XOR function from what we got in the previous slide. So I encourage you all to try that exercise at home, because I think it's informative to understand that when you're learning neural networks, there's multiple different choices of parameterizations of neural networks that all give you really, really good results. In this case, perfect classification accuracy for a potentially very complex nonlinear data set. And so this neural network only required one hidden layer, but it is very wide. It has 2 to the D elements in that hidden layer. And so we can also ask about the expressivity of the logistic activation function. Well, in the previous few slides, we instantiated this with the hard threshold activation function. But unfortunately, the hard threshold activation function is not differentiable. So in the future, when we want to do gradient-based learning, it becomes a little tricky to learn with that. And so what we end up using are things like the logistic activation function, where you'll notice that if you scale up the input to the activation function, you can start approximating the hard threshold function pretty well. But it continues to remain differentiable, so we can learn via gradient descent. So why do we care about expressivity? And what is it actually good for? So the truth is, we may often need a very large neural network to represent a function, but the fact that these are neural networks and the fact that neural networks are universal function approximators does not mean that we are guaranteed to approximate any function from empirical samples. So the original proof of universality is an existence proof. It says that there exists a neural network that if you had a magic genie to tell you what the right weights are, could do perfect classification that could approximate any function. But as practitioners of machine learning, the challenge we have is not the existence, it's the learnability of a neural network, which is how well can we use tools from optimization like gradient-based descent to train the parameters of this neural network so that they do good classification or regression or anything in the middle. And another concern that comes about is the fact that we now went from having one matrix and one vector of biases to having L of these. So we have a huge number of parameters. And if you think back to the case of polynomial regularization, you might wonder, aren't we concerned about overfitting? So do neural networks overfit, and how can we regularize them? And the answer to the first question is yes, they do indeed overfit. And the answer to the second question is that it's still research in progress. Like, there's lots of really clever ways to regularize neural networks, and how people do it is going to be a function of changing the structure of the neural network, adding explicit loss functions terms for regularization, and even studying the training dynamics of how the weights change over different epochs of learning in order to encourage some sets of functions in this hypothesis space over others. So there's no one answer to how best to regularize them, but we're going to talk about a really simple way that you should all know, and that's early stopping. So the topic of overfitting is not really well understood, and you can always apply L2 regularization, and in CSC 413 you'll learn a lot more advanced techniques for regularization. But for now, the one you should know is called early stopping. So remember, we always want to plot two things when we do any machine learning: the training loss over iterations of our optimization procedure, which is always going to go down, because as we do more and more optimization, we're always going to fit the training data better and better. But we also want to plot things like the validation error, the generalization error. What early stopping says is that you should plot your generalization error and then stop training your model when you suspect that the generalization error is starting to increase. That's it. Like, that's basically what early stopping says. So you look at your training curves, and in practice what you do is you often checkpoint these models as you go through training. And if you find that you've now had a huge spike in your generalization error, or you've started to overfit, you just throw away that last model checkpoint, go back to the previous one, and that's your model. And this is a really interesting way of regularization because there's no dependence on any explicit form of a loss function to add to our optimization objective. So we're sort of just using how well the model is training in order to determine when to stop. And in practice, we talked about different kinds of metrics like area under the receive operating curve, or held out metrics such as true positive rate, false positive rate, and you can use any of those as a proxy depending on the problem that you care about. So I'll pause here to see if folks have any questions about neural networks and essentially how they're constructed, how they're learned, how you can use hard threshold neural networks in order to approximate outputs from Boolean functions. We gave an explicit example of using the decomposition of the XOR function and constructed a hard threshold neural network to do perfect classification in that case. And I gave you the intuition for how to show that you can use a very wide neural network to approximate any Boolean function. Yeah.
Just about how we actually learn the weights that go into each of the like
Yeah.
layers. Is it just like we just do like square loss at the end, or is there like more complicated ways to get into that?
So we'll dive into learning for neural networks later, but like the basic idea is that you're going to define this loss function, and the loss function is going to change depending on the task you care about. Like if you're doing regression, you would do a squared loss. If you're doing binary classification, you would use a logistic cross entropy. If you're doing multi-class classification, you would use the softmax cross entropy that we learned today. And actually, that's one of the interesting things about neural networks, which is that you can have multiple different loss functions put together as well. Like you can use the same neural network to do classification and regression and multi-class classification, where all of you have 3 different output layers rather than just one. And I think a lot of work and advances in machine learning have benefited from this idea of the fact that there's many data sets for which learning a common shared representation is actually really helpful. Yeah. Right, so that's a really good question, which is what's really controlling the expressivity of a neural network model? So theoretically, a 2-layer neural network is a universal function approximator. But again, that's an existence proof, right? Like it says nothing about how hard it is to learn that function. And what we showed is that if you had a d-dimensional Boolean input, then the width of your neural network would have to be 2 raised to d. So that's an exponential growth in the size of a 2-layer neural network to be a universal approximator for Boolean functions. Now, the question then becomes, like, you know that the strategy is going to work, but you're going to have a massive explosion in the number of weights if you have to work with really shallow neural networks. And so what people do instead is that they learn much, much deeper neural network. And it turns out that you can do really, and this is an empirical statement. Like, I don't have theory to back this up, but practically all of the neural networks that we learned today are about 100 layers deep, but not very, very wide relative to the dimensionality of the input. And so it turns out by stacking very deep neural networks, one on top of the other, you're basically making your search problem easier and easier to find good weights. So for those of you who are familiar with things, with the construction of tools like ChatGPT or GPT-4, it's the exact same situation as a multi-layer perceptron, except instead of a linearity plus a nonlinearity, we're composing a much more complex operation called an attention mechanism, which you learn about in 413. But the principle is the same. You stack multiple of these attention mechanisms on top of each other in a transformer architecture, and repeating that computation in a large depth tends to give you tools like GPT. And again, we don't have good explanations for why these phenomena arise, but that's, I think, what's driven, like, empiricism has driven a lot of the research and development in neural networks in the last decade. Yeah?
My question isn't about neural networks and stuff. It's just we have a midterm coming in 2-ish weeks. So how do you recommend we prepare for it, and what's the content that's going to be covered?
So the midterm in 2 weeks is going to cover everything up until what we finish next week. For prepping for the midterm, next week in tutorial, there'll be a midterm prep session. And I will aim to release at least one, hopefully 2 midterm practice midterms with solutions for that from basically past years, for you to get a sense of some of the kinds of questions that have been asked in the past. So those are 2 good ways, but yeah.
Thank you.
All right. Oh yeah, you had a question. I think with 2 layers, it's one layer of hidden and then one output. Yeah. So that's it for today. Thank you, everyone.